So we'll be starting in a minute or two. Can someone please confirm if I'm audible? Uh, could you please confirm if I'm audible?
Yes, sir.
Okay, fine. So I guess we can start the live session for the week 4 for the course Introduction to Semiconductor Devices, which is taught by Professor Naresh Kumar Imani from IIT Hyderabad. And I am Anant Singhal, PhD student from IIT Jodhpur. So I'll be assisting you in solving similar assignment problems which are given to you in week 4 assignments, and that will help you in solving the assignment problems that are given to you this year. Uh, so let's move on to the course outline. So as we can see in the initial 3 weeks, we have already covered all the transport part. So maybe, yeah, so in the week 1, we have briefly talked about very basic of semiconductors, like why we choose, what kind of materials do we have, and other things. And from week 2, we started how the electrons or holes transport in the equations or in the semiconductor. And in week 3, we read about some of the key concepts such as uh, the components such as drift component, diffusion components, etc. And we got to know some of the key physics of the semiconductors. So now, so in short, if I like to maybe summarize up, so what we have done is we have done for, let's say we have some different type of semiconductors such as N type and P type. So we have read about the band diagrams. So if I talk about band diagrams, so we have a EC, we have a EV, and we have an intrinsic level in between. Similarly, we have for P type, that is EC, EV, and EV. So what we have read till now is for the N type of semiconductors, we know that the Fermi level lies closer to the conduction band. And for the P type semiconductors, what we have, the Fermi level lies closer to the valence band. Uh, I hope you already know the reasons, and we have already read about the Fermi direct statistics that tells about the probability of an electron being occupied at a certain states. Then we have already covered the density of states, etc. And all, and how this electron transfers. So let's say I have an type of bar and I have not applied anything. So how these electrons go from one end to another, that we have seen. And we have seen two main criteria in the last lecture, that is the drift part of the current and the diffusion part. So in drift, we know that this is due to the electric field, and this is due to the change in the concentration gradient, that is how it changes. And we got to know some of the relations such as Jn is nothing but nq mu n e. So this component is due to the what I can say is due to the drift. And then we have nothing but dn, yeah, some proportionality. So this is the diffusion component and this is the drift component. Similarly, we had jp, which will be similarly mu p and pq mu p. And similarly, the proportionality is rise with something minus dp by dx. And the total drain current or the current density that we have is the sum of these two. So this is what we have already covered. So now we are going towards the most important topics of this particular course, that is the junctions. So junctions means that we will be making certain semiconductor devices that you will be reading in the further classes. And we'll be initially starting with the PN junction. That means that we have a single bar in which we have different types of doping, and what happens at the junction of those doping. Then we have certain approximations that I'll be covering. Then what about the electric field of the junction, the built-in potential? What is built-in potential? I'll be telling you each and everything. And the most important topic is this. If you know how to draw a band diagram for any of the junction, then you will be able to solve any problem that will be given to you. So I'll be starting with the junctions only, and if you have any doubt or queries from the previous lecture, you can ask right now. Otherwise, we'll start for the junctions. So is there any query from the last lectures?
No, sir.
Okay, fine. And one more thing, I guess if you are already aware that we have a WhatsApp group in which we can have some doubts clearance. So if you are not able to join the WhatsApp group till now, maybe Om, you can share the WhatsApp group link in the chat box, and those who have not joined can join the group. So that will be better for each and everyone. So meanwhile he's sharing, I can start with the most important topic. So if you have any doubts in between, so you can just stop me and ask if I'll be able to tell you. So the main topic I'll be starting for this lecture is junctions. So the key points that we will be covering in the junctions are, first of all, we need to draw the band diagram. We need to understand how this band diagram is drawn. Band diagram, I hope you are already aware, that is the energy band diagram that I'm talking about. The second key point is the band bending. So the second key point is band bending when we join two materials. So initially we'll be talking about each and everything in equilibrium, that is we are not applying any external bias. So if I go like that, so let's say we have if you have any doubt, you can stop me there only, right? Consider that we have two materials. So let's say what I have done is I have joined two materials. This is material 1 and let's say this is material 2, this box. So we know that the concentration is given out by the multiplication of the density of states times the Fermi Dirac. So let's say this has G1 F1 and this has, let's say, G2 of the density of states and F2 the Fermi Dirac. So what we know that the Fermi function F1, can anyone tell how we can write the Fermi function? What is the formula? Quickly.
1 by square, 1 plus e to the power.
Yeah. So for Fermi level, let's say this has a, yeah, so that is fine. So let's say this has a Fermi level, you can mute yourself, EF1 and EF2. So this will be 1 minus EF1 by KT. And similarly, if I try to write F2, this will be 1 upon 1 plus exponential E minus EF2 by KT. So I hope this is all clear from the previous lectures there only. So now we know that, as I said, the electron concentration is nothing but it is given out by the multiplication of the density of states times the Fermi Dirac. So if I write the electron concentration, maybe I can write N1, not like that. So N1 is, let's say, G1 F1. And similarly, for the second material, we have something known as G2 F2. So now the whole concentration, if I say for this particular material, so can anyone tell what will be the whole concentration? Any guess? So maybe I can give you for P1. So it will be nothing but the occupancy of the hole. So that will be 1 minus Fermi Dirac of that particular holes or the electron occupancy. So similarly, P2 I can write as G2 and this will be 1 minus F2. Is this clear?
Yes, sir.
Okay. So if this is clear, so a key thing to notice is, as I'm talking about equilibrium, so what we know is the flux from left to right and right to left. Flux means the change of concentration from left to right and left to right and right to left will be equal. So that means N1 P2. So what we have P2 because uh, we will be having, I'm like taking the example, so this will be hole and this will be P2. So because this is a, for N1 region, we will have a minority carriers of hole and N2 will be equals to P1. So if I just substitute all the values, so we know that N1 is F1 G1 and P2 is nothing but 1 minus F2 times G2, and N2 is, we have already written, it is G2 F2, and P1 is G1 times 1 minus F2. No, it is F1. So if you can see, if I just write maybe the first term, so F1, so I can directly cancel out this G1, G2. So the first term will be F1 minus F1, F2. The LHS will be this, and this will be F2 minus F1, F2. This again gets cancelled out. That means the Fermi levels, the Fermi Dirac function is equal. What does it mean? So what I can write is 1 upon exponential of E minus EF1 over KT is coming out to be equal to 1 upon 1 plus exponential of E minus EF2 by KT. So can someone tell what does it implies? If I have these two equal, what does it mean? Can I say that EF1 is equals to EF2? Does it make sense?
Yes, sir.
Yeah. So that means at equilibrium, Fermi levels
Yes,
align.
yes. Equilibrium.
Yeah. So for if we even if we join two different materials, we will have a same Fermi level for both these materials. So this is the key takeaway from this particular thing. Is it clear to everyone? Because we'll be talking about the PN junction, so we need to know how to make the band diagram and why it is happening like that. So that is why this is a very basic overview that the Fermi level always aligns if we have a equilibrium condition. So moving forward, so let's say I have joined, okay, so there are some terms, maybe I can go through them. So let's say this is the vacuum energy level, and let's say if I make a P type of semiconductor here, this is EI, this is EF, this is sorry, this is EC, this is EV. And here let me take, this is EI, this is EC, this is EV. So let's say I have a P type of semiconductor, which I can write, so this will be EFP, and let's say I have a N type of semiconductor here. Let's say this is EFN. So the key takeaway what I'm trying to tell here is whenever we are joining these two bars, so this will be a P type of bar, this will be a N type of bar, and we are joining them. So whenever there is a joining, so what happens is electron will flow from material having higher Fermi level, higher EF, to the material having lower EF. Does it make sense? Do you understand what I'm trying to say? So if I have a P type of material and an N type of material, so we have N type material which is having a higher Fermi level. So all the electrons will travel from the higher Fermi level to the lower Fermi level. Is it clear what I'm trying to say here? Please respond if it is clear.
Yes, sir.
Okay. So now,
So,
yeah,
excuse me, sir.
yes, yes.
So, why does it always happen like that? Why does it flow from higher Fermi level to lower Fermi level?
Okay, so you can already see that we have a higher energy level at for a N type of semiconductor. If I'm talking about the PN junction case, and we have a lower energy for any P type of semiconductor. So we know that electric field or even any particle move from high concentration gradient to lower concentration gradient. Maybe I can give you a very basic example. So let's say we have a box, or we have a room in which we have, let's say, very close particles, and we have some minute particles like that. So we know that if we just leave the room, so what happens is these particles will always move more quickly as compared to these, because these already have some space around them. So what happens after some time, the room will be like this. So what happens, the movement of these particles will be more as compared to these particles. So this is what the analogy here also is. Because we have a higher concentration, or we have a higher energy level, we will have more electrons present as compared to this. So that is why the electron always moves from higher energy level or higher Fermi level to a lower Fermi level.
Okay, sir. Thank you.
Yeah, you can even take the example if that does not make sense. Let's say we have a water tank, something like that, and we have, let's say, two buckets of water we have, uh, which is having, let's say, this is bucket 1 which is having EF1, and this is bucket 2 of water which is having a lesser Fermi level, which is, let's say, EF2, or water level, you can just relate. So what happens is, there is always, to equalize this, there is always a motion of water from EF1 to EF2 to, so it is something like that. So that is why all electron always moves from a higher Fermi level to a lower Fermi level. So once we have stabilized the fact that the Fermi level will move to a higher Fermi level, to a lower Fermi level, and the second thing that we have stabilized is EF aligns at equilibrium. Like we will be having a same energy level if we are not applying any bias. So what I can do is, I can maybe quickly make again. Sorry. So this is EFP, and this is EFN. So what we have, just see that the electron or this Fermi level will come down to here, and these two will be in the same line because the Fermi level needs to align at equilibrium. So what will happen is, so now listen carefully, we need to have this Fermi level here to have this equivalency, right? Does it make sense? Just respond. Does it make sense to everyone that we need to have, that the first thing that we have considered is Fermi level will always align, like we will have a single Fermi level for each and everything, for a material at equilibrium. So what we need to do is this Fermi level always, the electron will come down from here to here, so we need to have this Fermi level aligned. Does it make sense?
Sir, why can't EFP rise instead of EFN just falling?
Yeah, so that is the thing that I have just told you, that EF of a higher level will always come down to a EFP because of this concentration gradient. Because we have a higher energy, so a higher energy particle will always move to a lower energy particle like this.
But the concentration on the P side is also rising. So then the Fermi level on that side could move to a higher energy also, right?
No, if the concentration rises for the P type, it will even go below. This will
Okay.
rise, but this will always go below. As you can see that even if I increase the concentration here, the Fermi level will not rise. It will go beyond the EV, right? It is not going up. This is going up, this particular level, if I'm
Okay.
increasing the concentration. So that is why what I was saying, yeah. So this needs to come down. So now just to have this a very, so what I'll do is I'll keep this each and everything same. So I have this EFP, and this has now come down, let's say, to align that. So I have a EFN here. So if I have a EFN here, I will have a EC here, maybe EI here. Okay, so maybe I'll redraw it, and I have a EV here. So what I have done till now is I have aligned the Fermi levels. So this is a single Fermi level now at equilibrium. So now I'll join them. This is EI, and this is EV. So this is what we call as band bending. Does it make sense to everyone? So what we have is this will always remain the same. ECEV will have always a energy gap of EG. Here also we will have a energy gap of EG, and maybe if I can take some other color. So this will always be EG by 2 since I'm talking about EI. So it will always be EG by 2 for both the bulk cases. Uh, and this, like here also we will have a EG. The difference will always be EG. Does it make sense? This is what band bending is. So what I have done is I have just aligned the Fermi levels for the P type and the N type, and we have got some bending. So if I make maybe a single diagram, let's say this is the energy level. So since this is P type, so this is ECEV. This is ECEV for P side. Now I have made the Fermi level also, so maybe I can draw EI, and the blue one is the Fermi level. Is it clear to everyone? Because this is the most basic thing, because we'll be going to maybe some more devices such as NPN junction, maybe a MOSFET. So everything will be done using this band diagram only. So if you have got the idea of how this PN junction is working, then you will don't have any problem in further devices also. Is it clear to everyone? You can type in the chat box or respond via opening your mic.
So here by equilibrium, what do you mean? Is it a thermal equilibrium or
Yeah, yeah.
electrical?
Thermal equilibrium. Is it fine with everyone? Uh, I hope that there are no further doubts. So we'll move to the topic. Sorry, we'll move to the topic of PN junction now. We have seen that how this band bending is happening. So we'll now see why it is happening and how it happens. So we have a, let's say, a single semiconductor bar in which one side we have P type and one side we have N type. So in P type, we know that the majority carriers will be. Can anyone tell what will be the majority carriers?
Holes.
Yeah, so holes will be the majority carriers. So we'll have some Na, and the majority carriers will be these holes, and the minority carriers will be electrons. Similarly, for N type, what we have is, maybe I can, yeah. For N type, we will have Nd, that is a positive donor acceptor ions, and the majority carriers will be electrons. So I'm denoting these electrons with the filled circles. So what happens? These electrons, and we have a holes at this side. So what happens? This electron, due to diffusion, will get attracted from to this holes, and this holes will get attracted to this electrons, right? So what happens? First of all, what will be the thing is, uh, so we will have a force on electron that is like this. So I'm writing Fe to this, and we will have a force on holes that will be like this. So I'm writing Fh to this. So once we will have the diffusion of electrons and hole, what happens is we have some region in which we are only left with this depleted carriers. That is, they don't move. So if I write something like this, so after the diffusion of carriers, we have some region in which we are only be having the depleted carriers. By depleted carriers, I mean that they do not move, they are not doing any movement, and the electric field will be, we know that it is from the positive to the negative side. If I talk about this region, so this region is known as the depletion region for a PN junction. So we had a single bar in which we had PN. So this junction is what we call as metallurgical junction. So this particular figure shows a PN junction. So it is important here to note that this entire box is a single semiconductor bar in which we have one region which is doped with Na, that is a high type IP type of impurity, and one side we have doped with Nd to form this P type and N type region. And this interface separation that we have is referred to as PN junction. Or to be in simple words, we have a step junction. So let's say I've taken some Na concentration here and some Nd concentration here. Again, this is position. So what we have an abrupt change in the concentration for P and N type. So that is why we also call it as abrupt PN junction. So what I mean, there is an abrupt change in doping for the P and N side. So this is P with having some particular Na value, and this is N with some Nd value. So initially at the metallurgical junction, what we have is there is a very large density gradient, that is this difference. And the majority carriers that I already told, the majority carriers electrons, these red dots that I'm making right now, they will begin to diffuse into the P regions, and the majority carriers holes, they will begin to diffuse to the N region, right? So if we assume that there are no external connections, I have not added anything, like both of these are at grounds, so then diffusion process cannot continue indefinitely, because there will be a time when this all the electrons are getting diffused to the P side and all the holes are getting diffused to the N side. So once it stops, so what happens is we are left with some of the junction we are left with some of the acceptor ions in the P region and some of the donor ions in the N region. And this is what we are calling it as the depletion region. Why? Because this region of net positive and negative charge ions near the junction, it is completely depleted of any mobile carriers, so we only have some negative and some positive carriers here. So that is why we are naming it as depletion region. So does it make sense? Is there any doubt in this particular thing?
So how would this appear in 3D? If you were to take a single block of silicon
Yeah.
and dope one side with accepted dopants and other side as with the donor dopants,
Yes.
how would be the doping done? Like from top or bottom, left or right?
Yeah, so we can okay, so that is a good question. So let's say we have a 3D block also. So what we generally consider that we have a uniform doping for the 3D bar. So if I'm taking a cube, maybe make in the next page. Yeah. So let's say this is a cube in which this particular cube, maybe I can just, yeah, so this shaded cube is for the P type and this non-shaded one is for the N type. So what we do is we do the uniform doping. So we have these acceptor ions uniformly available everywhere in this cube. So we can do the like doping. If we talk in fabrication terms, then it will be something different. But you can just say that we have uniform ions present at each and every point of this cube. Same goes with the acceptor, sorry, the donor case. Yeah. So there will be uniform acceptor ions each and everywhere present in this cube if I talk in terms of 3D. But for simplicity of analysis, we only go for 1D. That will be sufficient for you to understand the diffusion of carriers. Is that fine?
Yes, sir.
Yeah. So now we'll be talking about zero applied bias, PN junction. By zero applied bias, I mean that we have not applied any external voltage. So I guess we have already make sure that we know that how to make this band diagram. So what happens? Let's say this is P type, this is N type. So after some time, we will have only acceptor type ions left here. The donor type ions are left for the N type. We will have electric field direction like this. So if I quickly draw the band diagram, maybe you all can also try in your notebooks. So what we'll have is we have a aligned Fermi level because we are still at equilibrium. So this is P type, so it will be like this, and this is N type, so it will be like this, and we have some change in the energies inside the depletion region. So let's say maybe I can draw EI. So this is the change in the potential. So let's say I'm terming this for now. Okay, wait. I'm terming this as Q5P for now. Q is for the electron volts, and I'm terming this as Q5N for now. And this basically this Q5P plus Q5N is nothing but the what we call as built-in voltage. So I'll let you know what is built-in voltage, or I can write this as Q5BI if that is better. And this will be also built-in voltage because the difference is same. So I hope the band diagram is clear. I have already made it clear in the previous slides also. So now what I've talked about is this built-in voltage. So I'll be talking about this now. So calculation of this built-in voltage VBI. So what we already know that the electrons in the conduction band of the N region, what they do is they see a potential barrier. So what we have is we have electrons here in the conduction band. So what they see is they see a a potential barrier to cross or to go towards the P side. Similarly, the holes from I'm not sorry, holes are the let's say these are the holes. So they see a barrier to go to the N side. Uh, so what I can say is electron in the conduction band of the N region see a potential barrier in trying to move to the conduction band of the P type, and similarly holes in the valence band experience a potential barrier in trying to move into the valence band of the N side. So this is what this particular barrier that I have marked as Q5BI is referred to as the built-in potential or the barrier potential. We also call it as barrier potential. And this built-in potential maintains the equilibrium between the majority carriers in the N region and the minority carriers in the P region. And similarly between the majority carrier holes in the P region and with the minority carriers of holes in the N region. So this is very easy if we try to analyze mathematically now. So we know that from the above plot that this QVBI is nothing but equals to Q5P plus Q5N, or we can write VBI is nothing but equals to 5P plus 5N. So just try to be with me here. So we have EI this, we have EF this. I'm denoting this as EFP, I'm denoting this as EFN. It is still EI. So can I write 5P or Q5P as EI minus EFP? Is this equation clear to everyone? Is it clear that how I have written Q5P as EI minus EFP? Kindly respond. Am I audible, everyone?
Yes, sir.
So does this equation make sense that this Q5P is a difference of the EI at the P side and the EFP at the P side?
Yes,
If
sir. It's clear.
yeah, so if it is clear, so can someone tell what will be the Q5N? in terms of Fermi and intrinsic only.
EFN minus EI.
Yeah, so it will be EFN minus EI. So now what I can write is Q VBI is, we already know from this equation, is Q phi P plus Q phi N. So I'm just writing both the terms plus EFN minus EI. So this EI will get cancelled. So this VBI will be nothing but EFN minus EFP over Q volts, right? So now we'll do the general basic analysis what we do for P side. So let's say at P side, so I'm doing the analysis together, and let's say at N side. So I hope everyone knows this, that P is nothing but, for P type of semiconductor we have EI minus EF over KT, and for N type of semiconductor we have N equals to Ni EF minus EI over KT. This is what we have already read for single semiconductors that we have done in the previous lecture. Is there any doubt in this?
No, sir.
Yeah. So we know that for P type, the P will be approximately equals to, sorry, Na, and for N side, the N will be approximately equals to Nd. So what I can write now is Na is nothing but Ni exponential of Ei minus Ef. So we have already given that Ei minus Ef is this phi p, Q phi p. So I'm just writing here Q phi p over Kt. Similarly, Nd will be Ni times Q phi n over Kt. This is what we have already established in the previous slide. So what I can write here is phi p is nothing but Kt by Q. If I'm taking the log of both sides, it will be Na by Ni. And phi n will be Kt by Q ln Nd by Ni. Does it make sense to everyone? Any doubts here?
No, sir.
Okay. So if you don't have any doubts, then we know that what we have is, we have VBI equals to phi p plus phi n. So we'll just add the log terms. So we know that if we add the log terms, then there, wait, VBI phi p plus phi n. So I'm not writing it again. I'm just writing Kt by Q ln Na by Ni. So I can take Kt by Q common, and this is ln Nd by Ni. So we already know that ln A plus ln B is ln A times B. So using this, we have our built-in potential as Kt by Q. So we can do ln Na Nd by Ni square. Is it clear to everyone? So we can write this Kt by Q even as Vt, which is, we already know this is the threshold, the thermal voltage, which is given by 26 milli electron volts at room temperature at T is equals to 300 Kelvin. So is it clear, everyone, the VBI concept? Any doubts? You can let me know quickly if you have any doubts, if you have understood this VBA, you can let me know.
So does phi represent work function?
Sorry?
What does phi represent, sir? Does
Yeah,
it
yeah.
represent work
Okay.
function?
Yes, yes. It is a bug function. So, okay, I thought. So there are two different terms. I hope you are already aware. One is a work function and one is the electron affinity. Maybe I can explain that. That is a good question to have. Maybe I can explain this above. Yeah, so maybe here I can explain quickly. So we have two terms. One is a work function, and the second term is electron affinity. So work function is nothing but energy required to remove an electron from Fermi level, that is EF, to vacuum. And electron affinity, maybe the second, is energy required to remove an electron from EC to vacuum. So let's say I have this some energy level which is at vacuum, and I have now maybe the Fermi level is here. So the energy required to remove an electron from EF to vacuum is what we call as work function, which is Q times phi. Let's say semiconductor I am writing as S. And similarly, if I have a vacuum and let's say we have some conduction valence band. So this is so this energy that we are requiring, this is known as electron affinity, which is denoted by chi. So Fermi level to vacuum is always work function, and the conduction band to vacuum energy required is always electron affinity. So these are the two terms, like technical terms that we need to know. So this is what we have already. Sorry. So if this is clear, then we can have a very quick calculation of VBI. Maybe I can give you a question. So let's say we have a abrupt PN junction having the n side doping, that is Na, that is given by 3 times 10 raised to 16 per centimeter cube, and we have a Nd for n side which is 2 times 10 raised to 15 per centimeter cube, and we have it at T equals to 300 Kelvin. That makes the Vt as you can take it as 26 milli electron volts, and Ni we all know that you can take maybe the exact value, that is 1.5 times 10 raised to 10 per centimeter cube. So what you need to do, you need to find out the built-in voltage or the built-in potential. You can call it VBI. Maybe you can take 2-3 minutes. This is a very easy question, so that will not take long. And let me know what is the answer. Maybe I can give you the options also. Option A is, let's say, 0.64 volts. Option B is 0.86. Option C is 0.68. Option D is maybe 1.04. So you can quickly do it and let me know what is the answer that you are getting. Uh, and also confirm if you are trying or not. Otherwise, I'll just directly solve it. Are you guys trying? Please respond if you are trying.
Yes, sir.
Okay, fine. Any answers? Uh, Even you can tell what you have tried. That will be better. If anyone wants to tell what they are doing. Anyone? Is it not clear what we are trying to do here? Please try to respond.
Sir, applied that formula you mentioned about built-in potential. The calculation is taking time, sir.
Okay, so what is taking time? So, okay, I'll try to solve it. So we have this ln na nd by ni square. So if you have a calculator, I hope you have a calculator right now with you. So this is nothing but 26 milli electron volts. So I can write it at 0.026. And then ln na nd is 3 times 2 is 6 times 10 is for 31. And we have ni square, which is 2.25 times 10 is for 20. This is you just need to do. This will be the answer. So this is what it's taking time. Do you have a calculator with you right now, everyone? So if you just solve it, uh, so this is very easy. You just need to do the logarithmic of this particular number, and it will come out to be 0.68 volts, which is option C. I hope the way is clear, at least that this is how you need to do it. Is it clear? Kindly respond if it is clear.
Yes, sir.
Okay, fine. So we'll be moving ahead quickly. So what we need to do now, we need to do the second part for PN junction, which is the calculation of electric field. Sorry. Yeah. So electric field, we all know it is nothing but the gradient of dV by dx, the gradient of the potential. So what we have done till now is we have this P type and N type of material, and we had some junctions in which we know that at one side we had a doping of Nd, and one side we had a doping of Na. So if I write something like this, so this is X. So this is positive of Q and D. So if I try to plot the, sorry, charge density, so I'm multiplying the doping by charge, so that will make it as a charge density. Please don't get confused by that. And we have a net negative acceptor ions, which will be minus Q and A. So this is what we call as charge density, which is denoted by rho V, you can say. I hope this is not getting confusing. Is this clear? We have a uniform ND for the total N type of junction. Like for this region, we only are left with ND. For this region, we have NAs. So NA is mathematically negative and ND is positive. So that is why this is QNA, which is positive, and this is minus QNA, which is sorry, this is QND, which is positive, and this is minus QNA, which is negative. Is it clear? Uh, is there any doubt in this particular plot? Please respond if you have any doubt. Hello. I can write it mathematically also, that we have minus QNA from minus XP of X to 0, and from 0 to Xn we have QND, if it makes clear. Is it clear, everyone? Please respond. Hello, is it clear? I hope I am audible. Can someone confirm if I'm audible?
Yes, sir.
Okay. So now we know that for electric field or any calculations, what we have Poisson equation in semiconductors. This is the basis of semiconductors. What is Poisson equation? We all know this is d2v by dx2 is nothing but minus rho by epsilon. This is by rho v, or we can write this as dE by dx because E is dV by dx. It is again equals to rho v by epsilon. So this is what we'll use to calculate the electric field for the semiconductor. So what I can write is dE by dx is rho v by epsilon s. So what we can write here is integrating, this is rho v by epsilon s times dx. So let's say we know that at x equals to minus xp. So at this point we know that what we have is we have the rho as minus qna, and for this region we have the rho as qnd. So I'm writing it for the p side right now. At first of all, at x equals to minus xp we have a zero electric field. So from here to here we have a zero electric field, from here to here we have a zero electric field. The field that is changing is between the depletion region only. So at boundary condition at x equals to minus xp we have E is equals to 0. So first of all I am writing the solution, which is minus qna by epsilon s times x. The integration of the constant is times x plus c1. Is there any doubt in this solution? I've just put rho v as qna for the p side. So this is applicable up to 0 to minus xp. Is this clear, the solution? Please clarify if it is clear. Uh, Differentiation, sorry, the integration of a constant is nothing but cx plus some constant k. So this is what I have written. Is it clear? Hello, is it clear? Okay, so we know that E is equals to 0 at x equals to xp, so we'll put this and get the value of c1. So c1 will be 0 times minus qna, so this will get plus xp plus epsilon s, which will give me the electric field of minus qna by epsilon s x plus xp. So this is equation, let's say 1, and this only holds true for x is less than 0 and greater than minus xp. Similarly, we'll calculate the electric field for n side, in which we will have the electric field as integration of, now I'll take q and d by epsilon times dx. So that will give me q n d by epsilon into x plus c2. And similarly, we know that at x equals to x1, xn, we have E as 0. That will help me calculate C2, which will come out to be minus q and d xn by epsilon. That will give me the n side electric field as q and d by epsilon s. If I take common, so x minus xn. So let's say this is equation 2. Is it making any sense? Is it clear? The electric field at both the
Sir, how
ends?
the C1 and C2, sir?
Okay, C1 and C2. Okay. So I know that at the boundary we don't have any gradient. So maybe what I'm saying that at this boundary conditions I have E as 0. So once we have this equation for p side, let's say the electric field is a function of linear function of x. So minus Qna by epsilon s into x plus C1. So I have put in the boundary condition that at the value of x equals to minus xp, I have this E as 0. So if I put E as 0 and x at minus xp, I'll have the value of C1, which is some constant, right? So this is what I've written. So sorry, C1 will be negative of minus Qna. Yeah. So similarly, for the n-type region at x equals to xn, I have put it the same condition that E is 0 and I've got the C2. Is it clear? If you have still any doubts, you can ask.
Sir, at P side, the minus Q, uh, and that was should be positive. C1.
C1 should be positive, you are saying?
Sir, it was minus there. E equals to minus QNA.
Yeah, yeah. So I have put minus, sorry, I have put minus is there and I have put the value of x as minus xp. So this minus and minus is getting plus and it is going to the LHS. So that is why the finally I have a minus.
Okay. 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 Okay.
Yeah.
Okay.
So that is how I've got the electric field for the P side. And similarly for C2, I've put x as xn and E as 0. So if it goes to the LHS, it will be minus. So I have for both the sides. So if I plot this, maybe from minus xp to xn only. So we have the linear equation in terms of x. So at x equals to 0, we have some finite value. So this is how it looks finally, the linear relation. If you plot the equations directly, so this is how it will look. And this is what we call as the maximum electric field. So maximum electric field it at the middle of the junction or at the junction. Is it fine? The electric field plot? I've got two linear equations, so I've just plotted them. This is nothing much to delve into. Is it clear, everyone? The electric field, how it comes? So what we got is electric field is a linear function of x. And one more thing is at x equals to 0, the electric field is coming out to be maximum. And we can easily calculate that E max. So we can put the x0 for maybe in this case and this case. Both will be equal because it should be continuous. So we have got for P side, we have got minus Qna by x, sorry, by epsilon x plus xp, that is equals to Qnd by epsilon x minus xn. So at x equals to 0, we know that the electric field is E max. So E max is coming out to be minus Qna by epsilon xp, or it should be equals to minus Qnd by epsilon xn. Is it clear to everyone? Please respond if this thing is clear. Kindly respond because this is quite important to know. Is it clear? Okay. Is it not clear? I can explain again. So please respond. Hello. Am I audible, guys?
Yes, sir.
So is it making any sense? I've just put x as 0 here and got the value of Emax. So this is 0 and this is 0. So that is why I have written this, which is some constant value, which gives out a very key relation. So if I equate these two terms, Q and epsilon will get cancelled and NAXP is always equals to NDXN. So that means if we have a, let's say, higher Na and a lower Nd, what it will implies is Xp is greater than Xn. Do you understand what I'm trying to say here? If I have a higher doping on the P side, I will have a smaller depletion region on the P side. Do you understand, or should I explain again? Please try to respond, guys. You can be interactive in this particular uh, exercise, because this is a key concept you should have to understand it. Do you understand what do you
Sir,
mean by
the graph, this understand, but the graph you plot previously.
this plot? Okay, okay, fine. So we have a equation for n side which is q by epsilon nd x plus xp, I guess, something like that. And for this we have q nd by, sorry, so this will be na. This is x minus xn. I'm not, yeah. So what I plotted, we know that this electric field is a linear function of x. I have some constant multiplied, so y equals to mx plus c. So this c, the value of c is something which is minus q na times epsilon xp, which is some negative constant, right? Which is this, and the value of the slope is minus q na. So I'm writing m minus q na by epsilon. So that is why we have a negative slope with a negative intercept, which is also coming out to be E max that I've calculated. And similarly for this thing, we have a positive intercept because uh, what I have, so at 0, we have this QND by epsilon minus xn, which is this negative intercept, and the slope is again positive. So QND by epsilon is the slope of this particular thing, which is positive. So that is why we have a positive slope. And here the slope is negative, so that is why we have a negative slope. uh, I can explain you maybe a very simple math term. So let's say we have a equation which is y equals to 2x plus 1. So what we do is at x equals to 0, we have y equals to 1. And at y is equals to 0, we have, sorry, we have x equals to minus 1. Do you understand this? How I written this? So when I put x as 0, y will come out to be 1. And when I put y 0, x will come out to be minus 1 by 2. Sorry, 1 minus 1 by 2. Yeah. Does it make sense? Kindly respond.
Yes, sir.
Yeah, so if I plot this particular thing only for the negative axis, so at y is equals to 0, what I'm getting, at y is equals to 0, I'm getting x of minus 1 by 2. So let's say this is the point where x is minus 1 by 2 and y is 0. So this is the one of the point that I'm getting, and at x equals to 0, I'm getting a y of 1. So this will be the equation, right? So this will be the plot. Does it make sense? This will be the whole
Yes, sir.
plot. So similarly, we have the same equation here. We have a negative slope and a negative intercept. So that is why I'm getting this third quadrant, and this is the fourth quadrant for the positive slope. Is it fine now? Do you get the plot now?
Yes, sir.
Okay, so if you get the plot, I was explaining this thing which is key here. So NAXP is NDXN. So if I have a higher value of Na and a lesser value of Nd, so does it mean that XP will be less than Xn? Do you get this right? I'm asking everyone. So agar if the value of Na will be higher than Nd, then this value of xp, let's say 2 into 1 is 1 into 2. So let's say this is Na, this is Nd. So does it make sense that xp will be less than xn always? Uh, is it clear? Kindly respond if it is clear. Otherwise, I will explain again. Hello.
Got it, sir.
Okay, so that means that if I have a higher doping on either side, so if I have a higher doping on P side, then means that we will have a smaller depletion region on P side. Similarly, if I dope N side very largely, then we will have a smaller N side depletion region. That is what I want to say from this particular relation. Is it clear to everyone? Please respond now quickly so that we can move to the some of the problems. Is it clear to everyone? Kindly respond quickly. Kindly try to respond quickly because we don't have much time.
Yes, sir.
Okay. So if this is clear, then try to solve this problem. So we have a abrupt silicon PN junction with a doping profile as shown in this figure. Based on the doping profile, answer the question. So the first question is the corresponding charge configuration. So which one is the charge configuration? Kindly let me know quickly. I have already told you how to make the charge plots, that is the charge density plots. I have already told you how to make the electric field plots. So the first question is belonging to the charge density. So maybe you can take 2 minutes and try to explain me that why are you saying uh, the answer, whichever option you are choosing. So maybe in 2 minutes you can type your answers in the chat box and then maybe we can have the explanation after that. So again, please confirm if you are trying or not. Otherwise, I'll just solve it out. Are you guys trying? Please respond if you are trying. Hello. Please respond if you are trying. Am I audible, guys? Hello.
Yes, sir.
So are you trying or should I solve it by myself? If you can't talk, at least try to type in the chat box. This is very easy question. It should not take even 1 second to solve because we already know each and everything. Should I solve it by myself? So let me try to do it by myself for this question. So you can say you can see here we have a certain ND level and we have a certain NA level. So you can clearly see ND is sorry, NA is greater than ND in this particular question. And we already know that NAXP is equals to NDXN. So what comes out for XP and XN? Kindly let me know what is the relation that you are getting. Is XP higher or XN higher? Anyone?
X and higher, sir.
Okay, so NA is, yeah, NA is greater, so XN will be higher. So what will be the answer? You already have told me that XN is higher than XP. So what will be the answer?
Option B, sir.
Yeah. So this was very easy. I don't know why it is taking much time. Do you understand how it is option B?
Yes, sir. The
Okay,
Xn
so
out.
yeah. So similarly, if we have the same case, so what will be the electric field profile now? We already know that Xn is higher and Na is higher.
Option number A, sir.
Yeah. So this is very basic electric field and charge density profile plot. So let's move to the next question. So this is also what we have solved the similar question. So we have a abrupt silicon p-n junction in which we have the temperature given, room temperature. Na is given as 10 raised per 12, Nd is given as 10 raised per 16, Ni it is asking to take as 10 raised per 10, Kt by Q it is asking to take as 25 millivolts. So what we need to find? We need to find the built-in input voltage first, VBI. So do you want to try it? We have already done a similar question. Or should I explain it by myself? Please let me know quickly now. Hello, do you want to try it?
Yes, sir. Try.
Okay, okay, try. Any answers?
0.46.
Okay, so let's just check. So VBI is 25 millivolts. It is already saying so 0.025 ln. NAND will be 10 is power 28 and Ni square will be 20. So this will be 0.025 ln 10 is power 10. That will give me 2.303 into 0.25. So yeah, answer will come out to be 0.46 volts only. So that is good. So now for the same case, we need to find the depletion width of the N side. So okay, so since we don't have very much time, so I'll skip that derivation for the width of the depletion junction as of now, which is given in this particular question as 24.6 micrometer. I'll let you know some of the formulas that will help you solve it in a shortcut. So for the depletion width of the N side, what we have the formula, if we know the total width, it is Na upon Na plus Nd times the total width. And similarly for the P side, we have Nd upon Na plus Nd times the total width. And the total width is nothing but Xp plus Xn. So Xp is the depletion width on the P side and Xn is on the N side. If we have a PN junction, let's say, and the total width is W. So you need to find the depletion width on the N side. The total width is already given in the question as 24.6 micrometer. So quickly let me know the answer to this xn in micrometer itself. Are you trying again? Let me ask, are you trying? Please respond quickly if you are trying. Hello. Kindly respond, guys.
Solve it, sir.
Sorry.
So the values of like previous questions, values are same as previous
Yeah,
question.
yeah, yeah. So the question is same. ND, okay, I'll write again. ND was 10 raised per 16, NA was 10 raised per 12. The total width given is 24 micrometer. Let me try to write by myself now. So NA is 10 raised per 12. So this will be 10 raised per 16 approximately because it is very high, and W is, sorry, W is 24.6 micrometers. So this will be 10 raised per minus 4. So this will be 2.46 times 10 raised per minus 3 micrometer, which is option B. So you see one thing here. We know that ND in this given question is 10 raised per 16 and NA is 10 raised per 12. So ND is very, very high as compared to NA. So what it means is XN will be very, very less than XP. Do you understand this? The total width is 24 micrometer, and out of those 24 micrometer, almost everything is XP. 24.6 micrometer minus this 2.46 into 10 raised by minus 3 micrometer will be XP. So what I'm trying to say here is, let's say this is P and this is N. So the depletion width that we are having is something like this. This is XP, this is XN, which is very less. And similarly, we already know that the band diagrams or the potential profile. So this was the charge density, and if I plot the uh, electric field, so it will be something like this, which is very closer. So we have already done these things. So this is QNA, which is total negative, and this is QND. Do you understand what I'm trying to say? Even if you know the concept, you will be able to get the answer without even solving anything. We should know that Na will be very, very lesser. Sorry, not Na, Xn will be very, very lesser. So the next part was to calculate the depletion width of the p side. So that will be almost equals to the total given thing. Is it fine? Does it make sense? Are you able to get it?
Yes, sir.
Okay, great. So the magnitude, the next part of the same question is you need to find the magnitude across the PN junction. So again, we know that the maximum electric field we need to find here is QND by epsilon times Xn, or this is QNA XP by epsilon. This will give you the maximum field. So you have all the values, you can write anything. Okay, so maybe I can skip this calculation part and you can have the answer. I'll give you the answer. What is the answer to this question? So we have 72. The correct answer will be option A. If you will solve, you can do it in your home. If you have any doubt, you can ask in the next lecture for this particular question so that we can move forward now. Yeah, so this is a good question. So now what we will have, we have a P1 P2 silicon isotype junction. So what we have done is we have taken a silicon bar, we have doped it with P type, we have also doped it with P type. This is some higher doping of P side and this is some lesser doping. So these types of junction are called as isotype because we have same types of doping on the both sides. So as shown in the figure below, we need to find the correct band diagram. So you can try this out. You can take 2-3 minutes and let me know what can be the answer to this particular question. We have done a lot of exercise. I hope you will be able to answer it correctly. Try to see all the options and let me know what is the answer. You can take 2-3 minutes. Uh, do you get any idea or you want to explain? Anyone? Just let me ask.
Explain, sir.
Okay, so let me explain. Yeah. So let me ask you a quick question. Let's say we have a P type of semiconductor, which is something like this: EI, EC, and this is EV. For P type, we know the Fermi level should be close to the valence band. So let's say we had a Na of 10 raised power 16 here. So uh, can someone tell if I have a Na of 10 raised power maybe 18 per centimeter cube? So what will happen to the Fermi level? Will it go up? Will it go down?
Get closer to valence band.
Yeah. So higher the concentration, higher the Fermi level will go closer to the valence band. So here in the question you can see we have two types of region. One has Na1 which is higher, like Na1 is greater than Na2. So higher doping means we will have a closer Fermi level to the valence band. So you can see in case one what we have is we have, first of all, there it is at exotype and without any applied voltage, so it will be at equilibrium, so we will have a single Fermi level. So you can see for the option A what we have is we have a Fermi level. Here you can see the closer the Fermi level is closer to the valence band in this side as compared to this side. So what does it implies that we will have a higher Na at this side as compared to this side, right? Do you understand this? Please respond if you are able to understand this.
Sir, please repeat, sir.
Okay. So as I said that Na, if we have a higher concentration, let's say this is 1 and this is 2. If we have a higher concentration, then we will have the Fermi level closer to the valence band. What I mean is here I have explained. So let's say this is the Na equals to 10 raised power 18 case, and initially it was 16. So if I do it 18, what happens is, yeah, it will go closer to the valence band, right? So EF will shift downwards, right? Do you able to understand this first of all?
Yes, sir.
So if that is the case, so you can see in this case, maybe I can make it a bit smaller. In this particular case, these are the two gaps. So first of all, the Fermi level is always below EI. That means both of them are p-type, right? Right? Please respond.
Yes, sir.
And whichever is closer to the valence band is having a higher doping. So this is closer. So this is p plus plus. This is p minus. Right? Does it make sense?
Yes, sir.
Okay. So in the given question, what we have is in the left side we have a smaller doping, and on the right side we have a larger doping. So let's try to see option C first. So can anyone tell why option C is incorrect? Anyone?
It is for N type.
Yeah. We have a N junction here and a N plus junction here because this is closer. So this will never be correct. Okay. So now can someone tell why option D is incorrect?
EF is closer on the left side.
Yeah, EF is closer on the left side. And there is one more thing, that if the bands align, so it should be aligned at both the ends. It is not the case that it will go up. So now just try to see option B quickly. Na is higher on the right side here. EF is closer to the valence band. First of all, this is p type, this is also p type because EI is always above, and here we have a larger difference. So this is p minus, this is p plus plus, which is what is given in the question. So option B will be the correct answer. Are you able to get what I'm trying to explain, everyone? Like these are the very key concepts. If you are able to solve the band diagrams, you will be able to do the MOSFETs also.
So could you please explain what happened? What would happen at the junction? How the bending happens?
Oh, okay, fine, yeah. Yeah, so that will be great to explain. So let's say I have P here and P plus here. So first of all, I'm making it, this is EI, EF, sorry, this is EC, this is EV, this is EV, this is EC. So for P, let's say I have a Fermi level which is here, EF, and for P plus, I'll have a Fermi level here. So what we have seen is the higher Fermi level is always going to go to the lower Fermi level. So this will remain same. The right hand side, I'm making it again. This is EC, this is EI, and this is EV, and we have a Fermi level here, something like this. Okay, I need to maybe, sorry, let me rewrite. So I'll make it again. So this is EC, this is EV, this is EI, and we have this Fermi level for the right hand side which is having a higher doping here, right? So now this Fermi level will come down, this particular Fermi level will come down. So that means if I try to extend this, sorry, if this Fermi level will come down, then each and everything will come down. So we will have same EI and we will have the same EC. This is how the band bending will take place. So this will be EV, this will be EC, and everything is there. EI is there. Okay, like pardon for my drawing, I've made it a bit bad, but I hope you are able to explain how the band bending is happening.
Yes, sir.
Okay, fine. Yeah, that's great. So let's move ahead then. So let's now try to have some of the problems that you are given this week, assignment problems. So now I hope you will be able to solve this. So we have a PN junction in which the XP and XN are given. So XP is always given greater than XN. So first of all, the first question is you need to find the charge profile. So quickly let me know what will be the answer. We have done n type of questions now, so please don't take time now.
Option A, sir.
So I've got option A is one of the answers. Anyone else?
Option A, sir.
Okay. So we know that NAXP is greater than NDXN, and XP is given greater than XN. That makes NA lesser than ND. So option A, yeah, A will be correct because in this case NA is also lesser than ND. Similarly, okay, so there are some electric field plots also, so you can maybe got to know now that it will look something like this only if I ask for electric field. So I'm skipping that. So further we have doping concentration of a hybrid p junction is Na is given, Nd is given, and you need to find out the built-in voltage and the total depletion width. So will you be able to do it?
Yes, sir.
Yeah. So we already have the formula of this is Vt ln Na Nd by Ni square, and the total depletion width we can discuss in the later halves also, but it is something given out by 1 by Na plus 1 by Nd times Vbi. So you will be able to solve this. These are all numerical problems. So I'm not solving it. So I hope the concept is clear at least. Is it fine? Should I skip it? Maybe you can try to solve this problem, which is for an isotype junction, and let me know what is the answer. You can take 2 minutes. So we have a junction made of p silicon with Na1 of this value. Then we have a p-type silicon along with a doping of Na2 this value, and you need to find out the built-in potential again. So this will maybe clear a lot of concepts. So let me know what is your answer. Are you solving it or shall I do it by myself? Maybe I can do it because this is again very easy. So we know that from the derivation we got to know that it was q phi p plus q phi n for a p-n junction. I hope you remember this band diagram. This is what we did. So this was q phi n, this was q phi p, and the total of these two were VBI. So if I take a PP plus junction, what will happen as we have just drawn the band diagram? So let's say this is the Fermi level. So we will have some q phi p here, and we will have the q phi p in the same direction. So I can write maybe this is q phi p plus. So the VBI that we will get, the difference is now will be phi p plus minus phi p. I hope you get this. This is the main thing to capture here. So VBI will be phi p plus minus phi p instead of plus. It will be difference. Are you able to get the same? Please let me know if this is clear. This is important. Hello.
Sir, please repeat again.
Okay. So for a PN junction, we had this EI, and for the VBI calculation, when we were doing, what we did is because of this difference of the conduction band was Q phi P plus Q phi N. But for a PP plus junction, what will happen? This VBI will now be, because since EI is on the same ends, so we will have a Q phi P plus and we will have a Q phi P. So the difference of these two will now give us the VBI instead of the addition, because sorry, because we are not going below this. Sorry, I again. We are not going below the Fermi level. So there is no addition of the phi p. There is in fact a difference. So that is what I'm saying, that for VBI, for a p plus junction, we will have a negative sign. That is, sorry, any doubt?
Yes, sir.
Yeah. So if I try to solve now, so it will be Na1 by Ni minus Na2 by Ni. So minus, we know that we need to divide the log terms. So this is how we got Na1 by Na2. Whichever is higher will come on the top. Is it clear to everyone?
Okay, sir.
Yeah. So you can solve it maybe. So it will be 0.025 again. At room temperature, it is asking ln. Na1 is 10 is per 17. So whichever is higher will come on the top. So you will get, I guess, 0.025 ln 100, which is 0. Sorry. Yeah. Yeah. Where was I? Yeah. So 0.05 ln 10, 0.05 times 2.303, 15, 15. So it will come out to be something, I guess, 0.12, if I'm not wrong. Maybe option A is correct. You can check the calculations, but yeah, the concept is the same. Is it clear, everyone?
Yes, sir.
Okay, fine. Then we have done almost all the questions of PN junction without the application of any bias. So if I go quickly on the top, then you can see all the topics are covered. So we have done for each of the topics. So in the next week, we'll be covering the PN junction if we have applied a certain bias. So we have some of the topics. If we have certain bias, then there is some band banding under the applied bias. So how it will change, and we'll now move towards the ideal diode equations, that is the current equations that we'll have for PN junction. So is there any query for today's lecture? Anyone? So if there are no queries, then we can dismiss today's lecture and we'll meet the same time at the next week for the further topics. I hope it makes some of the understanding better for you for this lecture, because as we are going forward, we'll have some more complex topics. So if you have any doubt, you can ask in the WhatsApp group. You can mail me anytime. I have already shared the mail with you. And
Uh,
yes,
WhatsApp group your number, sir.
okay. So like one of the student has a link, so maybe you can type in the chat box. Till then, I'll stop the recording.
Please upload it, sir.
Yeah, yeah. So I'll upload it in like 10 to 15 minutes.